This is a video on inverse trigonometric functions. We are in Unit 3 of our Precalculus OER course, and Section 3.8 is about inverse trigonometric functions. If you remember, the trigonometric functions are periodic functions, and as periodic functions, they repeat every certain amount of time. The period for sine and cosine is 2 pi, and the period for the tangent is pi. This results in those functions not being one-to-one because they do not pass the vertical line test. Since horizontal lines cross the graph of the tangent function for certain y values infinitely many times. As a result, in order to create the inverse trigonometric functions, we must restrict the domain. The key to restricting the domain is that we want to make sure quadrant 1 is always part of the domain restriction because it has the property that all trigonometric functions are positive. So we will have a positive sine, a positive cosine, and a positive tangent. The domain restriction is a part of the domain that generates the full range of the function. So for the sine function, we achieve the highest value in the range of 1 when the value in the domain is pi over 2, and we achieve the lowest value, -1, when we are in the negative rotations in terms of x. So we achieve a -1 that is attached to the part of the graph for quadrant 1 when the x value is -pi over 2. Therefore, the domain restriction for the sine curve will be quadrant 1 and quadrant 4 with negative values. So from -pi over 2 to pi over 2 inclusive, so that we can have the maximum and the minimum values of the sine. The range will be the full range of the sine function, and it will be covered through that domain restriction. And when we invert the function, the domain will be -1 to 1, a value of sine through the range of values of sine, and the range of the inverse sine function will be some angle from -pi over 2 to pi over 2. Again, remember that the inverse sine function will return only one possible value of a rotation that has a given sign, and that possible value is only one possible solution of the infinitely many solutions that could potentially have a particular value of sine we are interested in. Now, the inverse function swaps x and y. So instead of 0, 0, we will have the point 0, 0. Instead of pi halves with 1, we will have the point 1 with pi halves. And instead of -pi halves with -1, we will have the point -1 with -pi halves. And the wave, instead of wrapping around the x-axis, will actually be wrapping around the y-axis, which means if I were to continue, it would be going around the y-axis, and it wouldn't be a function, of course. The input to the inverse sine function is a value of a sine, some number between -1 and +1, and the output is an angle from -90 degrees to +90 degrees. For the cosine, the domain restriction that must include the first quadrant and cover the full range also includes the second quadrant. This is a conveniently attached part of the graph that actually covers the whole range from 1 to -1. We achieve -1 when the rotation is equal to pi. Therefore, the domain restriction for the cosine will be from 0 to pi inclusive. 0 achieves a value of the cosine equal to 1, and pi achieves the value of the cosine equal to -1. Inclusive means closed at pi as well as 0. The range will have to be the full range of the cosine function, -1 to 1. And the inverse cosine function will have a domain of -1 to 1 and a range of angles from 0 to pi, inclusive 0 to 180. The points on the graph of the inverse cosine function will be 0 to 1 will be 1, 0. Pi halves with 0 will be 0 with pi halves. And pi with -1 will be -1 with pi. And the graph will be wrapping around the y-axis, will be a wave that if I were to continue it, it would not be a function, but will be wrapping around the y-axis. The input to the inverse cosine function is a cosine value, some number from -1 to 1, and the output is an angle from 0 degrees to 180 degrees. The domain restriction for the tangent that will require that the first quadrant is included in the domain restriction will actually have the rest of the branch between the two asymptotes. So it will have the asymptote at -pi/2, the asymptote at pi/2, and only one branch of the tangent function will be considered. The domain is -pi/2 to pi/2, but it is open because the tangent is undefined at the endpoints. The range is the range of the tangent function, -∞ to infinity. Therefore, the domain of the tangent, inverse tangent, will be -∞ to infinity, and the range will be some angle between -90 degrees and 90 degrees. Not included those answers. The graph will have a horizontal asymptote, y equals pi/2. It will have another horizontal asymptote, y equals -pi/2, and it will go through the point 0, 0, the point 1 with pi quarters, the point -1 with -pi quarters, and the input will be a value of a tangent function, any real number, and the output will be an angle between -90 degrees and 90 degrees. Now, again, remember that actually the domain restriction restricts the answers that your inverse trigonometric function will return. There are many more angles that have been excluded from the graphs in order to obtain a one-to-one graph that will pass the horizontal line test. Therefore, the inverse trigonometric functions are just tools to get us one answer, and from those we can look at more answers. Now, let's practice a little bit. Another notation for inverse sine is arc sine. Arc sine means the arc, the rotation on the circle, that has sine equal to negative square root of 3 over 2. As a reminder, the arcsine function only returns in quadrants 4 and 1, negative angles, not positive angles. I'm looking for one angle in quadrant 4 that has negative square root of 3 over 2 for a sine. And as I look here in my graph, in my trigonometric circle, the sine is negative square root of 3 over 2 over here. This angle is 300 degrees, but as an answer for the arcsine function, it has to be a value between negative 90 and 90. So this value will be negative 60 degrees. In our calculator, we will keep our calculator in degrees, or negative pi over 3 when we write our answers for a test. Arc cosine of square root of 2 over 2. As a reminder, the inverse cosine function returns an angle from 0 to 180. There are many other angles, infinitely many, in fact, that have a cosine of square root of 2 over 2. An alternate notation is cosine inverse of square root of 2 over 2. Since the cosine is a positive quantity, this will be in quadrant 1. And in quadrant 1, an angle that has cosine equal to square root of 2 over 2 will be right here. And that angle is 45 degrees, or 5/4, if expressed in radians. The inverse tangent of negative 1, and again the inverse tangent has a domain restriction between negative 90 and positive 90. If the tangent is equal to negative 1, negative 1 means quadrant 4, but a negative angle in quadrant 4, not a positive angle like shown in our packet. I'm looking for a tangent equal to negative 1, which means that the cosine and the sine have identical absolute values, just different signs. That angle is at 315 degrees, but again, I'm looking for a negative rotation. So from 0 to go to 315 degrees, that will be negative 45 degrees, or negative pi over 4. The inverse sine of negative square root of 3 over 2 is the same with arc sine of negative square root of 3 over 2. So it will be negative 60 degrees, or negative pi over 3. It will be helpful to start searching in your calculator to see if you can find these functions. We are not allowed to use graphing calculator in our classes, so we don't have this, but my graphing calculator has buttons for the sine, the cosine, and the tangent, and then second, and that button will give me the inverse function. I want to make sure that I'm always in degree mode. Radians are very difficult because they are irrational numbers. It's very easy for me to convert from degrees to radians. So I keep my calculator in degree mode, and then I just do second and sine. That will give me the inverse sine and negative square root of 3. Divide by 2. And the answer will be negative 60 degrees, and I will translate it to negative pi thirds. Negative cosine of, inverse cosine of 0. And again, looking on my formula packet, the cosine is equal to 0 in 90 degrees. So if I use my calculator, it should tell me 90 degrees. And I will write on my paper pi over 2 when I'm answering a test question. Let's check here also. Inverse cosine of 0. The answer should be 90 degrees. Now, be very careful. The inverse functions have domain all real numbers. The tangent has some exceptions at the asymptotes, but the inverse functions do not return all real numbers for an answer. They return within the domain restriction. So let's look a little bit of how the composition of inverse and the regular trigonometric function will look like, or the composition of any inverse trigonometric function and some other trigonometric function will look like. So what is the angle? Inverse trigonometric functions are angles. What's the angle that can be returned by the inverse sine function that has sine equal to the sine of pi thirds? So when I am on the circle in my packet and I'm at pi thirds here, the sine of pi thirds is equal to square root of 3/2. And it's asking me what angle that is an answer from the inverse sine function will have that sign. The inverse sine function returns angles in quadrant 1 and 4. This angle is in quadrant 1. Therefore, the answer that I should get is pi/3. Now, of course, I can check that in my calculator. I can say what is the inverse sine of the sine. And remember, I'm in degree mode, so I want to put that as 60. And the answer will be 60 degrees. The next one says, what's the inverse sine? Which means, what is the angle that has a sine equal to the cosine of -3 pi quarters? Now, -3 pi quarters is here. It's in quadrant 3. And neither the sine nor the cosine, the inverse functions, return anything in quadrant 3. Especially the inverse sine does not return anything in quadrant 3. So I don't expect to see any angle related to -3 pi quarters. However, let's see what we are looking for. So the cosine of -3 pi quarters, when I am in my formula packet, is negative square root of 2/2. So this value is negative square root of 2/2. So the question that they are asking me is, what angle has sine negative square root of 2/2 in the quadrants that the inverse sine provides answers to? And the inverse sine provides answers from -90 degrees to +90 degrees. And this sign is negative. So if this sign is negative, the answer I will get is in quadrant 4, and it will not be a positive angle in quadrant 4 from 217 degrees to 360 degrees. It will be a negative angle in quadrant 4 from -90 to 0. Now, looking again on my circle, and let's pull up our formula packet instead to have a clean circle. Looking at the circle here, negative square root of 2/2 for sine in quadrants 1 and 4 this way is this angle right here. And this angle right here is the 7 pi quarters, but in terms of negative, so that will be here, 7 pi/4, but in terms of negative, that is -45 degrees to get there from 0. So that answer will be -45 degrees, or let me move this quadrant for this way, or -pi/4. The next one is the inverse tangent. We won't be able to answer this with a rational number, unfortunately, or even a fraction of pi. If you remember, the inverse tangent function returns in quadrants 1 and 4 from -90 to +90. The sign of -π/6 is, let's go back to my formula packet. -π/6 is -30 degrees, so I'm here in this location, and the sign here is -1/2. So this is asking us for an angle in quadrant 4 that has a tangent equal to -1/2. But unfortunately, none of the angles that we know has a tangent equal to -1/2. The familiar angles provided to us in our packet, multiples of 30 or multiples of 45, have tangents equal to 1 or √3/3 or √3. We don't know an angle that has a tangent equal to 1/2. So in my calculator, I could find a decimal approximation. I could say, what's the inverse tangent of -1/2? But that is not the exact answer. So it is approximately 26.5 degrees, approximately, but the exact answer is this one. So this is the angle that has a tangent equal to -1/2, and that's the exact answer. But if they want a decimal approximation, rounded maybe to the nearest tenth of the degree, that will be approximately -25.6 degrees. If they want an answer in terms of radians, I will either convert the angle to radians or I will change my calculator to be in radian mode. So I could potentially convert this to radians. Times pi and divide by 180. And in radians, that will be -0.46 radians. Remember, radians doesn't have a unit. It is just a placeholder. So I can use inverse functions to solve right triangles when I don't have the angles, but I do have the lengths of the sides. Now here in this triangle, they have given me little a to be 5. It is the side opposite to angle A. They have given me little b to be 15. It is the angle opposite to angle B, the side opposite to angle B. And I can use Pythagorean theorem to find little c. So little c will be the square root of 5 squared plus 15 squared, which is the square root of 225 and 25, 250, which is 5 square root of 10, if I simplify that. And therefore now I can use inverse functions to find the angles. Now, I know that C is the 90-degree angle, so I don't need to find that. And I'm not going to use the work that I did, the 5 square root of 10, because I'm not sure I did it all correct. I will only use the two sides that I was given from the problem. And if I go in my packet, under right triangle trigonometry, the function that has the opposite and the adjacent is the tangent. And the tangent of A is 5/15. So let me write that here. So the tangent of A is 5/15, and the tangent of B is 15/5, because 15 is the opposite of B and 5 is the adjacent of B. Therefore, to find A, since I am in quadrant 1, A will be the inverse tangent of 5/15. And And B will be the inverse tangent of 15 over 5. So approximately to the nearest tenth of the degree, that will be inverse tangent of 5/15. Approximately 18.4 degrees will be angle A. And B, hopefully, will be the complementary. So if I go, what's the inverse tangent of 3, which is 15 divided by 5, I will get 71.6 degrees approximately. And it is true that 18.4 degrees plus 71.6 degrees add to 90 degrees. And I have solved the right triangle.